nonlinear structure formation. So after a discussion on the perspective. So yeah, over to Kanan. So I will conclude now.
Okay, thanks, Tavumeda. So we'll have our tutorial for today now, and for that we invited Kanan Kumar Datta from Presidency University, who will elaborate on the different line of sight effects on 21 centimeter signal. So I'll not take any more time. So over to you, Kananda. So you have the permission to share. Yeah, okay. Please go ahead.
Okay. Okay, thank you, Raghu, and all the organizers for inviting me to give talk on this. So let me share my slides. Is it visible now?
Yes, yes.
Okay. Okay, so I have been asked to discuss the line of sight effects on the 21 centimeter signal from epoch of reionization and cosmic dawn. So before I go into the details about what is line of sight effects such as redshift phase distortion, light cone, and Alcock-Paczynski, let me briefly tell you about what signal we are considering and what are the effects on how those line of sight effects affect this signal. So we have already heard from Somnath's talk about the basics of 21 centimeter signal. Let me quickly go through it for the completeness of this topic. So as you have already heard, the basic measurable quantity in 21 centimeter cosmology is the differential brightness temperature, delta TB, which is a function of the direction, the direction at which you are looking at, and the redshift. Redshift is also the proxy for cosmic time. And this differential brightness temperature is defined as this is a difference between spin temperature and CMB temperature, that is T gamma, multiplied by tau, which is optical depth, 21 centimeter optical depth, and the whole quantity is divided by 1 plus z because of the redshift, because everything is getting redshifted if you are looking signal from redshift z. So the details derivation you have already gone through from Somnath's talks. So spin temperature here, it is basically quantifies the relative population of ground state neutral hydrogen atoms in triplet and singlet state, and defined as this N1, which is triplet state number density of neutral hydrogen atoms, and N0 is the singlet state number density of neutral hydrogen atoms, and here Ts is the spin temperature, and T star is a combination of some constant which is 0.0628 Kelvin. Okay.
Ananda, can you make the slides full screen?
Okay.
Yeah, the second option.
Okay. Is it okay now?
Okay. Yes.
Right. Okay. So now, so the picture, the picture at the left hand, it shows basically the observations concept. So in the background, you have cosmic microwave background signal, which is coming from redshift 1000, and those 21 those cosmic microwave background radiation passes through intergalactic medium, and it reaches to us. And in between, if you have neutral hydrogen cloud, then that cosmic microwave background signal will be altered, and that the change in the brightness temperature of the cosmic microwave background signal is the quantity of interest here, which is basically delta TB. So it's basically the change in the temperature of cosmic microwave background signal if there is neutral halogen. That is the quantity we are interested in, and that is called differential brightness temperature. So difference between the CMB temperature and the temperature that we observed by the telescope, right? Now you all already have gone through the derivation of differential brightness temperature, that is delta TB, and this can be written in this form, right? The delta TB, so it's a combination of many parameters you have already seen. It is a function of cosmological parameters like omega baryon, omega B, Hubble parameter, that is H, omega matter, that is the total dark matter and baryonic matter. It is also a function of quantities related to large scale structure, that is the fluctuations in the baryon density, also on the peculiar velocity. And I will come to these two parts in detail in a few slides. Signal also depends on the ionization fraction, the overall ionization fraction, and spin temperature. Both of these quantities are function of redshift and the spatial coordinates. For example, cosmological parameters they are constant. It does not depend on which direction you look at. However, the ionization fraction and the spin temperature and also delta B, that is the fluctuations in the baryon density, all are dependent on X and Z. And basically these quantities contain information about underlying astrophysical processes like fast stars, galaxies, black holes, dark matter models, fundamental physics. So in principle, this delta TB, it contains enormous amount of information about the background cosmology, about the large scale structure of the universe, as well as the astrophysical processes arising due to the fast luminous sources. So if we could measure delta TB, we can extract enormous amount of information about the epoch. And that's why it is one of the most promising tool to study the epoch of reionization. Okay, now we have to understand the signal, and in order to understand the signal, we have to model it numerically. You can also do analytical calculations, and you will learn more about those analytical calculations by Somnath in next 2 lectures. But analytical calculations have some limitations. You cannot model it in detail, and in order to understand the signal properties in detail, you have to model it numerically through numerical simulations. And there are many simulations that can do that can simulate the differential brightness temperature maps at different redshift. Okay, so I'm not going into that because there are a separate set of lectures by Ovinas who will discuss how to simulate, what are the different steps for simulations. So he will discuss that. My goal here is to discuss the processes that change this delta TB, particularly the line of sight effects that change this delta TB, and as well as the various statistical quantities. Okay, so now let me tell you briefly the basic pipeline for simulations. Okay, so here this picture you see here, it shows the pipeline for simulations. So the top left picture, so we start with dark matter distribution simulation. So basically that I think Ovinas has already discussed, that we have an n-body dark matter simulation that gives us distribution of dark matter at different redshifts. That covers the epoch of reionization, cosmic dawn, and sometimes post-reionization epoch as well. So once you run n-body dark matter simulation, you have a distribution of particles. That means you know the particle positions x, y, z for each particle. So you have a large number of particles in a box, and after you do the simulation, you have at the end of this simulation, you have particle positions. Also, you have information about the velocities of those particles, that is Vx, Vy, Vz. So this is a 3D simulation. So you have information about all three directions. And so this is the n-body simulation. And then you have an algorithm that that helps us to identify the dark matter halos. So dark matter halos, we mean that the locations where you have higher number of dark matter particles compared to the surroundings. And so there is a prescription how to identify those high density regions. And those regions, so we identify those halos, and we have mass, total mass of that halos, and also the location. And so why do you do that? Because we believe that those high density dark matter halos are the hosts of, they are the hosts of fast luminous sources. So we identify these dark matter halos. You see these red circles, those are the locations of dark matter halos. And then we believe that those are the hosts of fast luminous sources like fast stars, galaxies, or black holes, right? And then so according to their mass and various other conditions, we assign certain luminosity to those halos. And then those luminous sources will emit radiation. So basically it will emit UV radiation, X-ray radiation, and all kinds of radiation they will emit. And the ionizing radiations, that is the photon with energy 13.6 electron volt, they will escape the halo environment and enter into the intergalactic medium. And then they will start ionizing the neutral hydrogen and also helium. Okay. So that's how this reionization starts. So basically you need another simulation to actually simulate the ionization field. That means you have to know which locations will be ionized and which locations will remain neutral. That you have to know, and that can be done using various techniques. Like there are full radiative transfer simulation, also semi-numerical simulation that Avinash will explain to you. But for timing, let's assume that we have a semi-numerical or radiative transfer simulation. And if we run that simulation, that will give you ionization field in 3D box. So like the one that I have shown here. And then once you have ionization fields, in order to convert that ionization field into the measurable quantity, that is differential brightness temperature, you have to use that formula, that differential brightness temperature formula, delta TB, to convert that ionization field into the delta TB field. Okay, so now once you have differential brightness temperature field, basically you know delta TB at each grid points. Also, at the same time, if you retain the particle information, you also have the particle locations and also the velocity of all of them. Okay. So that is about the basic structure of your simulation. Details will be explained to you by Avinash. So please follow Avinash's lectures.
Hello,
Yes.
Ananda, sorry to say, but I'm not going to discuss the reionization simulations with them this time. This time it will be discussed by, I think, Barun.
Okay, I see.
So I will cover up to FOF only the large scale structure simulations.
I see. Okay, sorry. So then follow Borun's lecture. Okay, but these are all connected.
What should be the box size? It should be larger enough to have signal, or it should be small enough?
Okay, so this for reionization purpose, if you want to simulate 21 reasonably, I mean, if you want to calculate power spectrum or other statistical quantities, the box size should be large, very large. Large means at least 100 megaparsec.
Correct. Co-moving.
Co-moving size. Yes. If it is bigger, it is better.
Correct. Correct.
Otherwise, you won't be able to capture the large scale feature of the signal, which will be targeted by these upcoming telescopes like SKA or LOFAR or MWA. So if you want to mimic LOFAR observation or SKA observation, you have to have a bigger box, at least 100 megaparsec or bigger.
The other question was related to your previous slide. Can you go back to your previous slide?
Which one? This one?
Yes, exactly. Huh.
Yes.
So you mentioned that people do radiative transfer and then they calculate simulated 21 centimeter in the post-processing step. So are there any simulations which can do both, simulate the 21 centimeter in radiative transfer step itself?
For 21 centimeter, if you want to calculate 21 centimeter signal, you don't need so what is the crucial input is you have to have ionization fields.
Correct.
And once you have ionization field, then it is very simple. You don't need radiative transfer.
Correct. No, I mean, I was just following this Somnath's lecture in which he mentioned that there could be effects of the Wothausen field effect, which will couple Lyman alpha photons to the 21 centimeter. I mean, the states, the excited states. So I was curious because this field, the Lyman alpha photons, which will be developed by these Taylor sources, which will happen in radiative transfer step, right? So how does that coupling will happen now?
Okay, now so for Lyman alpha coupling part, that part you probably need radiative transfer.
Correct.
So there you have to calculate the coupling coefficient, Lyman alpha coupling coefficient, that is X alpha.
Yes.
Right. And that depends on how much Lyman alpha photons you have in a certain location.
Correct. That's right.
And for that calculation, you need radiative transfer.
Exactly. That's right.
Yes.
So,
and once you have X alpha, this coupling coefficient, then you can simply use it to calculate your 21 centimeter signal.
Okay. So you so this
post processing.
So radiative transfer output will also give you this Lyman alpha coupling, and then you can use that. Okay.
Yes. But nowadays people don't do radiative transfer for Lyman alpha because it's a very complicated calculation.
Correct.
So what people do that they have let's say there's a source and they assume some kind of escape fraction.
Correct.
And then so then that radiation will pass through IgM, right? But for that accurate calculation, you need radiative transfer. But nowadays, people assume it to be falling as 1 by R square kind of thing.
From the sources,
Yes, I don't know if there is any group trying to do radiative transfer in that.
Thanks.
Right. Okay, so now if you now as you realize that at the end of your simulation you have a 3D box that gives you delta TB, but now all those boxes are simulated at one particular redshift, right? So like this, so you have x-axis, y-axis, and then you have line of sight axis. But again, this line of sight is also the entire part of this line of sight is simulated at one redshift. That's a fixed redshift, and that is called coeval boxes. However, if you observe a 3D volume, your box is not at one particular redshift. It has a spread in redshift, right? So let's say you are observing in a frequency band from 150 megahertz to 170 megahertz. That corresponds to some lower redshift and higher redshifts. So your box actually spreads in redshifts. It is not a fixed redshift. But your simulation gives you box at particular redshift, fixed redshifts. And there is a problem. Because then if you assume it, if you use coeval box, that is the entire box is one redshift, you are not calculating things correctly. Okay, so you have to actually consider the fact that your box, 3D box spreads in redshifts, and along the redshift, your neutral fraction statistical properties of the H1 fluctuations could change substantially. And also, so for example, let's say you simulate a 300 megaparsec box, and that 300 megaparsec length along the redshift, it will correspond, it will extend from redshift 7.51 to redshift 8.53. So it is not at redshift one fixed redshift. So it has spread in redshift delta Z equal to 1. So, and that you cannot ignore, because from redshift 8.53 to 7.53, things can change drastically, like neutral fraction, statistical properties, bubble size, and everything will change. So you have to consider that fact into account, and that kind of box is called light cone simulation. So you have to actually incorporate that. So now how do you incorporate? How do you implement? So you have what you have coheval box, delta TB box at a fixed redshift, and you can simulate for different redshift like Z1, Z2, Z3, like Zn, and that covers the entire epoch of reionization, cosmic dawn, whatever range you prefer. But then you want to simulate a light cone box, and that is shown in the bottom figure. So let's say you want to simulate a box around redshift 8, and it spreads from 7.5 to 8.5. So you so what you do, you divide the entire redshift range into number of slices, and then you fill up each slide. So let's say this called the extreme left side corresponds to redshift ZL. So you fill up that slice from corresponding coeval box. So let's say this is ZL. So you just take out this slice and fill it here. Then next redshift slice corresponds to ZL plus 1. And so you fill up the corresponding cells, corresponding slices from the subsequent box. So like that, you take each slice from different coeval box and fill your light cone simulation. So that's how you do, you simulate the light cone boxes. So now it is more realistic compared to the coeval box, right? So you can do that. So it's not that difficult to implement, and we have done it already. Yes.
So I had a question. So when you are talking about the coeval box, so you have different redshifts.
Yes.
Across the coeval, the z direction of the coeval box is not redshift, but actual physical distance, is it?
Right, right.
So then why are you saying that you take the corresponding slice? Can I not take any slice in the z?
You can, there is actually, this is not, there is one complicacy here, right? And so also, you can take any slice. So for the, let's say for ZL, consider ZL, slice corresponding to ZL. So and that and the second coeval box corresponds to, let's say, ZL. You can take any slice from that box. All corresponds to redshift ZL, right?
Right.
But then when you go to the next slice, it is ZL plus 1. Okay. Now, let's say you have taken slice number 1 from Z2. Now, when you go to ZL plus 1, you cannot take slice number 1 from Z3, because those slices are essentially same realizations with some changes. Yeah, but you have to take the next slice, which is basically your neighboring slice and completely different realization.
No, but then if I take the central slice of each of the block boxes, they will. So when you say Z2 for the coeval box, which slice of the coeval box corresponds to that redshift? Is it the first or the central one? Or
no? So all slices corresponds to ZL, but then you cannot. You can take any slice for the first slice, but when you go to the next slice, for example, the question that you are asking now. So can you pick up middle slices from all boxes and fill up my light cone box? No, you cannot do that, because the underlying the density field is same in all middle slices. So you cannot take. So it is basically the same slice, but with some evolution that you don't want. In your real observations, you just imagine you are observing at redshift 6, 6.1, 6.2, and those slices are not same realizations, but they are at different time and different realizations.
Hello. So I also want to join the discussion. So if I have understood correctly the doubt, so we cannot take the middle part of every, but if I choose middle from the first box, then I have to choose the next slide of the middle slide from the second box. Is that true?
Yes.
Okay.
Yes. Yeah, that's true.
May I add something? Since this is a periodic boundary condition in the coable simulation, the coable box, so you need to be cyclic. Like if you choose the first, so from n, if you choose the nth slice from the first, then you need to choose the n plus 1th slice from the second, and
Yes.
like
Yes.
it should be cyclic.
Yeah. So you think about it, Prasun and all other participants, think about it. And then if you are still not convinced, you can come back to me.
And about another thing, it's a statistical thing, right? So the mode which is present in the first slice, you cannot take the same mode. So we need to take. So you need to think in Fourier space. So you are taking the modes, right? So you cannot take the same mode from all the boxes. You need to choose the different modes, right? It's a cosmological thing. So think in cosmological terms.
Kanan, when you do this actually in practice, you interpolate, right? Because you cannot save the boxes to such a large number of boxes, right? 1024 or something like this.
Yeah, so there are two methods. One method is this interpolation. But the another method that Rajesh has developed, Rajesh, and also you are part of that, is that we don't basically interpolate, but we just pick up chunks from each coval box. So in that sense, let's say from 1 to 2, index number 1 to 2 is basically same. It is basically same redshift, the entire from 1 to 2 index.
Correct.
So and then 2 to 3 the same slice. So if you want to be more correct, it's better if you have more and more slices.
Correct. That's
then
right.
the gap between 1 and 2 will be lesser and lesser, and then you are heading towards more accurate light cone simulation. But then of course we have limitations. We don't have infinite number of coval boxes. We have around 50-60 coval boxes that covers your UR history. Then of course you cannot and we have investigated it. It is so it gives you reasonable results. It converges. So let's say we have 50 boxes and we have 100 boxes, and we calculate statistical quantities like part spectrum, and it converges more or less.
And which quantity you do this use this light cone on? Is just on the brightness temperature or neutral fraction?
So in the interpolation scheme, we do it for brightness temperature.
Brightness temperature.
But for the second method that Rajesh has developed, we basically do it in the particle levels. Basically, we pick up all the particles that is lying between 1 and 2 and fill it in between 1 and 2 in light cone. So you have particle positions and also velocities, because that will be required to implement light cone and peculiar velocity effect simultaneously.
Correct.
There are other effects that I'm going to discuss now. Okay. If you want to implement both together, you have to have velocity information as well.
Yeah, but then velocity, how will you interpolate? Because this will be different.
No, you don't interpolate. That's why I'm saying you cannot interpolate velocity. So that's why you have to select particles from there.
Okay.
And whatever velocity they have, you have to just use that.
Correct.
Yeah. Okay, so I think let's move on. Okay, now this is one of our results. So the left panel, basically your Koival box. The box is entirely simulated at one redshift. And then the corresponding light cone maps is this, the right panel. And you see the x-axis, it spreads from redshift 9 to 9.7 approximately, centered around redshift 9.3. And you see in the left hand panel, that is Koival box, you see this bubble that looks much bigger in Koival simulation. But if you actually implement light cone effect, it appears actually smaller. And that is what expected, because when the bubbles which are at the far end of your box, it corresponds to earlier time. And the bubbles which are near end at the front end of your box, it corresponds to later time. That means it has more time to grow. So the bubbles at nearer end will appear bigger, and bubbles at the far end will appear smaller. And that's what you see. This bubble appears smaller, and this big one appear bigger. And that is the actually effect of the light cone. Another important aspects, very important aspects, that when you implement your light cone effect, it basically makes your signal not ergodic. That means your signal is not homogeneous along the line of sight anymore, because at nearer end it corresponds to redshift 9, at the far end it corresponds to redshift 9.6 or a little higher than that. And it could change from case to case, but near end is always at lower redshift, and far end is always at higher redshift, that is earlier time. And during that time, your universe could change drastically. So you break your homogeneity. Also, you break your isotropy. So basically, the two basic cosmological principles, that is, the universe is homogeneous and isotropic, that are broken if you implement the light cone effect along the 3D along the line of sight directions. And also your box is not periodic. So these three things actually are the implications of light cone effect. However, I must say that your signal is always homogeneous and isotropic if you consider just one slice perpendicular to the line of sight. So that is important. So along the perpendicular to the line of sight, your signal is homogeneous and isotropic. But if you consider the line of sight direction, your signal becomes inhomogeneous, and also your signal is not homogeneous, also it is not isotropic and not periodic. So these features actually very important when you discuss the statistical estimator, and I will come to that later.
Sorry,
Yes.
Kananda, can I just add something? Yes. So when you say inhomogeneous, it means statistically inhomogeneous.
Yes, of course.
The signal the statistics of the signal is inhomogeneous. It's a ergodicity. Yeah.
Yes, of course. Statistically homogeneous. Yes.
Yeah.
Yes.
So
thank you. Okay, so now that was about light cone effect. Another effect is red sea phase distortion. And so before I go to discuss the red sea phase distortion, let me tell you the Hubble law. The Hubble law tells you that any astrophysical objects, the velocity of it is proportional to the distance, right? So if an object is at less distance, velocity will be lesser, and if it is at higher distance, the velocity will be higher, and that is proportional to. So let's say if you have an object at distance d, velocity vh, then the velocity for an object which is at 2d, velocity will be 2vh, just double, and that is the Hubble law. And this Hubble law basically inherently assumes that your universe is isotropic and homogeneous. However, if you look at the actual matter distribution in your universe, it's very clumpy, it's very inhomogeneous. You have voids, you have filaments, you have clusters. So let's say the same Hubble law, let's say this object is, if an object lies inside a void, it will feel attraction from the nearby high density peaks. This is local attraction, gravitational attraction, and because of that attraction, it will have an extra velocity, and which is called peculiar velocity, right? So this, for example, this particle is in the void, so it will try to move out from the void because of the attraction from this surrounding density, high density regions. Second particle will have a very strong gravitational attraction from this nearby high density region, cluster region, like that. So in addition to the Hubble velocity, you'll always have additional velocity that is arising due to the local density, over density or under density, and that is called peculiar velocity. And here I show it is using these red arrows, like these are the extra, these are the extra velocities arising due to the local over density, and that is called peculiar velocity. So your right. So yes. Now, so this peculiar velocity will change the redshift measurements, right? Because now, in addition to the Hubble velocity, you will have extra velocity, and that will change the redshift measurement. In cosmology, we calculate distance of an object using redshift, and of course using a cosmological models. Now, so the distance, the way we calculate distance, this is the moving distance by using this equation. That is, it depends on cosmological parameters, also on the scale factor, that is on the redshift. Now, due to the peculiar velocity, your measured redshift is now different. So your calculation of the distance will be different. So actually, if you go look at the previous picture, the apparent location of an object will be different if you look at, if you are in redshift space. So for example, this object may appear here, this object may appear here, this object will also may appear here, and the location will change along the line of sight direction only. It will not change perpendicular to the line of sight, because perpendicular component will not alter your apparent locations. So basically, your particle locations will be rearranged because of this peculiar velocity, and this new location can be calculated using this formula. This is S is your new location. This in redshift location in redshift space. R is the real location, and this correction 1 plus Z by HZ into V, that is basically correction due to your peculiar velocity. So it can be negative, positive, both, because V can be positive or negative. If it is going away from you, that means it will be always be positive. If it is coming towards you, it will be negative, right? So accordingly, your location in the redshift space will be different. So you can use this formula. So now in simulation, you have velocities, right? I have already discussed. You have velocity information already. So you can actually, from simulation, from real space box, all those boxes are in real space. Now, if you want to convert them into redshift space, you can simply use this formula, and this is what it is used to actually do that. Of course, here V is assumed to be very small compared to C, which is a very good assumption. Now, here you see this cartoon picture. So if you have a spherically symmetric objects in real space, it may appear compressed in redshift space. Your density will be enhanced. So things are getting compressed in a smaller volume, but the same mass. So it will be enhanced in density. And so that means your fluctuations will be enhanced. So your power spectrum will be more, basically the dark matter power spectrum. And this is called famous Kaiser effect. So Kaiser in 1987, he actually proposed this. And so this is actually seen in large scale distribution. But if you go to small scales, you have slightly different effect. That is also red space distortion effect, but their velocity is so high because of this kinetic motion of the particles. Instead of getting compressed, it will appear elongated. I'm not discussing that, but that is called finger of God effects. I'm not going into that. Fine. So now, how do you implement light cone and redshift space distortion together? Okay, so now what you have, so at the end of simulation, you have particle distributions. That means locations of your particle x, y, z. Also, you have velocities information, right? And also you have coheval boxes at different redshifts. So first, what you do, you create light cone boxes the way I have explained it to you earlier. Now, once you have light cone boxes, you have velocities for each particle. So what you do from your Cartesian coordinate, you have to move to the actual angle and frequency coordinate. So angle. So in observation, we always measure things in angle and frequency. We never measure in Cartesian coordinates or in coherent coordinates. We always measure in angle and frequency coordinates. So you have to convert your simulated boxes, which are in coherent coordinates, into angle and frequency coordinates. How do you do that? So it's simple. Theta x and theta y your angular coordinates, and that can be easily calculated. See, x is your coherent coordinates, and if you divide by the distance, that's coherent distance, you will get the theta x. Similarly, you will also get theta y. But if you want to convert in frequency, you know that you know the center, you know the redshift of each particle, and so from that redshift, your original frequency is 1420 megahertz. That is the original frequency, and from that redshift you can calculate the observed frequency. And so this is a formula. So this the last term n dot v is basically the correction due to the peculiar velocity. So you have velocity information, and you have to consider the line of sight velocity, not the entire velocity. So line of sight velocity will contribute to the redshift correction, and that's what you, and this second term is basically the Hubble velocity, right? So you from your coherent coordinates, you go to the angle frequency coordinate, and there you calculate the density. So see, everything you have in your frequency and theta coordinate, and frequency theta coordinate you calculate the density, and from that density is basically in redshift space density. So now you see. Sorry, so this bar is obstructing the image. How do I remove it? Do you see this bar, this zoom? Sorry.
No, I think zoom bar is only visible to you. You cannot see
Okay.
it.
Okay. But I cannot see the lower part of your image. Let's see. Sorry. Right. So now this this is an example. This the left hand panel is basically simulation in coherent coordinates, but then I convert it into theta frequency space, and it is also automatically implements light cone and as well as the redshift space distortion. Okay, so now I am done with I have the quantities in redshift space, the density, differential brightness, temperature, everything in density, and then I want to. The next important thing is that power spectrum. You have already heard about power spectrum. So basically, power spectrum is the primary target of all upcoming and ongoing radio experiments, and because it is very it is easier to detect. So the power spectrum is defined as this. So you have delta TV map, and delta TB is different at different locations, right? And then so basically, if you just take one, if you move from one along one line, your differential brightness temperature can change like this. It is not same everywhere; it is fluctuating. So the standard picture to decompose these fluctuations is in terms of Fourier modes. So we this kind of fluctuations we decompose in different Fourier modes. Like longer wavelength, smaller wavelength, and also the amplitude may change. And also these Fourier modes, the phase of these Fourier modes are also different, right? So we decompose this in different Fourier modes, and this amplitude of those Fourier modes is delta TB1, delta TB2, delta TB3. You have like n number of Fourier modes and their amplitude. So the part spectrum is basically you take delta TB and delta TB, delta TB at two different Fourier modes, you just multiply. These are complex number, of course, so you have to multiply accordingly. And so this is how you define part spectrum, and which has been explained by Tapoma already. So basically, if your two modes are different, then your part spectrum will be 0. And so K1, K2 has to be same. And then if you have some non-zero part spectrum. So basically, the part spectrum PHK, it tells you the amount of fluctuations you have in a particular Fourier mode, right? So let's say if you have uniform density, then your Fourier transform will be 0. So part spectrum is 0. If you have only large scale fluctuations, your small, that means part spectrum will be very high at small k values. So k means here k is essentially the inverse of your length scale, essentially, right? So I'm not going into the detail about the part spectrum, but remember that part spectrum is the primary quantity that will be targeted by upcoming and ongoing telescopes, and all these analysis will be based on this part spectrum and some other statistical quantities. So it is important that we discuss part spectrum and the effects of all these line of sight effects on the part spectrum.
Kanan,
yes.
So when you convert this coordinate, co-moving coordinate to angle and frequency, do you do it on the grid or do you do it on the particles?
No, we do it on the particles, particle to particle.
Yeah. So when you calculate the density, does the mass conservation holds for the box now?
Yes, yes. So the way we calculate the density here, yes. So you see, so basically we are not changing the mass. All particles are there, so mass is not changing. What Correct. Is happening is it's basically the particles are rearranging themselves.
Okay.
So let's say one particle is there in on a particular cell, and when you implement this redshift phase distortion, that particle may not be there in that cell. It may go elsewhere, either in higher index or lower index.
But when you convert it to signal, ultimately, do you convert it into grids? This particle information?
Yes, ultimately, if you want to calculate part spectrum, you have to convert them. Ultimately, you have to convert them into grids.
So that's my question. So when you convert now the particle information into grid information, yes. Now there is a smoothing length associated with each particle. So that will change with the redshift, right? That will not be constant with redshift. So how do you account for that?
No, when I convert them,
CIC, Avinash told you, we take the contribution from all particle to the grid with the weight to the distance.
Oh, okay.
CIC, simple. Avinash,
yeah, okay, it's a CIC. It's not a smoothing. It's not a smooth particle hydrodynamics here.
No. It's CIC. No. Distance. You calculate the distance from the grid and weight.
Okay. The other question is this: RC is the center of the box, right? The distance from the observer to the center of the box, or what?
Which RC you are talking about?
Theta x is equal to x divided by RC.
Yes. Yeah. So that, yeah. Yes.
So it's from the observer on Earth to the location. I mean the redshift. You convert it into RC, right?
Yes.
Okay. Yeah. Thanks.
Yeah. In principle, it should be. So this is RC is the distance corresponding to the central redshift. In principle, it should be RC corresponding to that redshift only, but that connection is not very high, so we keep it.
You can do that. That's a simple enough.
Yeah, yeah.
Thanks.
Ananda, I had a related question.
Yes.
So when you are converting at each slice, the particles at each slice, you are converting them to the theta x and theta y.
Yes.
But with the time evolution, it may happen that a particle that you have considered at the ith slice may come to I-1 slice in the next redshift. Right? So then you may, the number of particles may increase or decrease like that.
Yes. Yeah. That may happen. Yes.
So that can change a little bit of your mass.
Yes, that that change a little bit. Yes, I agree, but not much. We have checked it.
Okay.
Yeah.
Okay. So you have to make the redshift slice big enough, for example, to avoid that, is it?
But if you make it big enough, then there is another problem. Because
no, I mean,
then
that gives you a minimum size of the redshift slice that you can take probably. Because if I take it very small, then probably all particles will be available in the next redshift. I mean, half of the particles will be available in the next redshift slice.
Yeah, sometimes they may cross 2-3 slices also. You don't know.
Okay.
Right, because velocity is can be very high, and then
then that also has a effect on the peculiar velocities you are calculating.
In principle, what you are saying, yes, but we have actually checked it with standard picture. Like we know that is peculiar velocity, your part spectrum is enhanced by 1.87, and we have checked it, and it is actually so. So the effect is not much. Okay. Okay, so now I think it is already 4:30, so I have to finish the last part. Okay. Okay, so this is basically again. So as Prakash was already asking, so we have things in frequency and theta coordinates. We have to convert them back into Combing coordinates, because in order to calculate part spectrum, we have to move back things from theta x to nu, and then we can again do like this kind of reverse transformation. So we do it and then calculate part spectrum, and you see this part spectrum in the left panel. So left panel shows part spectrum as a function of k, and this solid line part is the part spectrum from coeval box, and this dashed line is the part spectrum from light cone box. Sorry. And you see this effect is not that important at small scales, that means at large k, but it can be very strong effect at small k. And we see actually this is a paper by Rajesh, and we see that a factor of 4 boost in the part spectrum at the largest scale, that means the smallest k available. And of course, this is just an example. It could vary from simulation to simulation, model to model, at what stage of reionization you are looking at. But at least we have checked it, that it's a large scale effect. And so in the right panel, actually, we saw the light cone effect as a function of neutral fraction, the global neutral fraction average. And you see that this dashed line is the light cone part spectrum, and this solid line is the no light cone, this coeval box part spectrum. And here we have used a bigger box, that is 607 megaparsec box. And we see the boost can be a factor of 5-6. So that's a huge. And so one cannot ignore, of course, consider this effect. Right, and then this part spectrum in redshift can be written like this. This part spectrum PH is a combination of part spectrum, and the total neutral hydrogen delta TB part spectrum is a part spectrum of hydrogen, neutral hydrogen density part spectrum, neutral hydrogen cross part spectrum, hydrogen part spectrum. And they are combined, and you see this mu square. Mu square means it's a here it is defined. It's a cos theta. It is cos theta. That means the angle basically there's a k z by square root of kx square plus ky square. So now this as I said, this redshift space distortion is a line of sight effects. So it introduces anisotropies in the power spectrum. So the power spectrum is not only function of k modulus, but it is also function of at which direction you are looking at in k space. So mu, it's a function of mu, and in linear theory you can write it like this, but in nonlinear theory it changes, and you have to do proper simulation. And I'm not going to discuss that. So you can, if you're interested, you can go to our papers and look at the results. And so here I show just one result from our recent from our work, that it shows the ratio between redshift space power spectrum and no redshift space power spectrum as a function of neutral fraction, and you see the ratio can be up to factor of 3. That means because of the redshift space, power spectrum can be enhanced by a factor of 3 at neutral fraction 0.1 or so. At later redshift, it is not that important an effect because your bubbles are so big that it basically all the high density regions are ionized. And that means the peculiar velocity effect is strong around the high density regions. And those regions are giving you zero signal. So that's why your redshift space distortion power spectrum is not different from the not redshift space power spectrum. So that's one important point to keep in mind. The last effect that it is Alcock-Paczynski test on the inverse signal. So, so what is Alcock-Paczynski? So in 1979, Alcock and Paczynski wrote a paper and say they basically argued that like they argued as follows. So our observations is done in frequency and angle, right? We always measure redshift and angular scale in some form. Now, in order to actually convert this frequency and theta into co-moving coordinates, you have to use this kind of relations. So let's say you have an object, 3D object, and its line of sight distance is delta r parallel. So delta r parallel is essentially delta nu, that is your frequency difference in observations into r nu prime. And this r nu is co-moving distance, and r nu prime is the rate of change of co-moving distance as a function of frequency. And its size in perpendicular direction, that is delta r perpendicular, can be calculated using by theta into r nu. Theta is the angular size of that object, and if you know the distance, the co-moving distance of that object, that will give you the delta r, that is the co-moving size in the plane of the sky, right? Now these transformations, so you measure things in delta nu theta space and you convert them in co-moving space using this relation, and these quantities are basically cosmology dependent. Basically, you have to know the co-moving distance to that object, and the distance, the way you calculate cosmological distance is by assuming some cosmological models and also cosmological parameters, right? So the distance estimation and cosmological parameters actually decide the delta r parallel and delta r perpendicular. Now, if your cosmological model is wrong, or if your parameters that you choose like omega matter, omega baryon, or dark matter, dark energy, if those parameters are wrong, then this conversion will be wrong, right? So that means even if you have an intrinsically isotropic object, let's say you have a perfect sphere in co-moving coordinates, but it may appear anisotropic because of your wrong selection of your cosmological parameters or the cosmological model itself. So, and that is a problem, because nowadays we believe lambda CDM model. but you are never sure that is the correct model. There are also issues with that. So if it is not following, if our universe is not following lambda CDM model, or at least at very high redshift, then this conversion can be wrong. And your isotropic, intrinsic isotropic objects may arrive anisotropic. Also, this spherically symmetric quantities like the power spectrum or 2-point correlation functions. So Tapumai has explained you 2-point correlation functions. So 2-point correlation function is basically it is same. So 2-point correlation function is a function of separation between 2 points, right? Now it doesn't matter whether that separation is perpendicular to the line of sight or parallel to the line of sight. If your inverse is isotropic and homogeneous, 2-point correlations function should be same along the line of sight or perpendicular to the line of sight. However, because of this conversion thing, because of your wrong cosmological assumption, this 2-point correlation function may not be same, or this kind of thing may introduce anisotropies in the power spectrum. So now, if you really know that this is perfectly isotropic, you can impose that condition and put constants on your cosmological parameters, right? So that's why it is important. So, for example, as I have already shown, this your redshift space distortion effect is not that much important at lower redshift at the end of your reionization, and also small scale light cone effect is also not very strong. So you can select those scales. Those scales are really isotropic and homogeneous, and see if there is a break. If you see some kind of anisotropies, even in the in that signal, you can actually impose statistical isotropy to constrain your cosmological parameters, right? So that is how it is. So it has been used in galaxy redshift survey in baryonic acoustic oscillation, but nobody has studied it in detail in the context of EOR 21 centimeter signal. So this is kind of open problem. One can look at this in detail, how Alcock-Paczynski test or effects can be used to constrain your cosmological parameters, or how that affects the signal in total. I have discussed all 3 line of sight effects. And as I try to explain you, these are very important. So I'll stop here, and if you have any questions, I'll be happy to answer.
Yeah, Kananda.
Yes.
Yes, Kananda, I think the similar kind of effect can be also produced due to redshift space distortion. So how will you distinguish between the two? Hello.
Yeah. Hi. Yes, Anjan. Yes. Yeah. Right. You are right. So there are three different effects that can influence your signal along the line of sight, like redshift space distortion,
right,
Alcock-Paczynski, and also line of sight.
Right.
Yes, it is. It may not be that easy, to be honest. But as I tried to explain you have to find a particular scale, K scale, and particular redshift where redshift space distortion effect is minimized. For example, our simulation indicate that at the later stage, redshift space distortion is very negligible. It's not that much. So you can select lower redshift 7 or 8 or 6 maybe. And also the light cone effect is also minimized at small scales. At large scale, you have strong light cone effect, but small scale like K equal to 0.5 or 1, it is also minimized. Then, so that means those signal at those scale will be very isotropic. So that's my speculation, wild speculation. No one has done it extensively. So
for
open problem. So you can actually go and check.
Galaxy survey. For galaxy survey, basically, you can analytically model light cone as well as redshift space distortion. And if there is a deviation, that may
point towards
coming from
yes. Okay. Thank you.
Yes.
But for 21 centimeter, no one has done this sort of.
Yes, no one has done.
But
that.
we cannot analytically basically model the light cone and AC space distortion for 21 centimeter.
There are raised hands.
Yeah, please go ahead and unmute
Yeah.
yourself.
Hello, am I audible?
Yes, Orgudeep, yes.
Okay. I just have a small confusion, which is, so in your previous slides, you have mentioned about the comparison between Quavel box and the light cone effect. So what I understand is that just using the Quavel box in simulation, or rather in any concept, is problematic because there is a range of redshift with the sizes. But I don't understand what are actually the advantage of using the light cone effect, because yeah, that the results are the map for the light cone effect shows some results, shows some other features in the plots. But what are the actual advantages of using that?
No, Orgudeep, there is no question of advantage. This is in order to accurately simulate your signal, you have to consider the effect. Otherwise, you are doing things wrong. That's what I tried to point out. So this is a real effect. So when you observe a 3D volume, let's say you observe with GMRT, and you use a band from 150 megahertz to 160 megahertz. So that corresponds to redshift 8.5, let's say 8 to 8.5, right? So it's not a single redshift, it's a range of redshift, and then it will be there. Your signal at redshift 8 will be much evolved signal compared to signal at redshift 8.3. So you have to consider it. There is no question of advantage or disadvantage.
There is nothing called Quavel. Basically, you cannot observe Quavel volume.
Yeah.
You always observe light cone volume. So the Quavel is just it's an approximation of the actual thing.
Yeah, sure. Yeah. Okay. Thank you.
So Kanan, all your simulations that you have shown, or the results that you have shown, they are all for dark matter only simulations?
The simulation. So let me go to the slides. Yes. So we start with dark matter simulation.
Okay.
Pure dark matter simulation.
So my question is maybe to both Kanan as well as Tapomai, is that whether there is a large scale offset between the baryons that you see and the dark matter, because if there is, then there will be a bias, right? I mean, you assume in this case that the baryons are just following dark matter.
Yes, we assume but I think people have checked it so see, this is simulation at redshift 6 or beyond that. So that means redshift 6, 7, 8, 9, 10 at this redshift range, and they are at large scale. I'm not talking about small scale. Large scale H1 more or less trace dark matter. So there may not be huge bias.
So at small scales,
there may be there. Also at later redshift, there could be also bias.
So when you say your power spectrum in co-eval and redshift space matches at small scale, that is for only dark matter only, but you don't know whether it would match for the baryons as well, right?
Okay, small scales means the scales I'm talking about is 0.51 in this range. Small scales, extremely small scale, that is k equal to greater than 1, or at those scales I don't know. Maybe our simulations we need to model it properly, more accurately.
That's right. Yeah, I mean there would be pressure smoothing in the
yes,
as a result, the specular velocities would be much different for dark matter compared to the baryon.
Then you have to see, Prakash, see that in that case you have to even treat specular velocity differently, because it is not, in that case it is not Kaiser effect, but it will be more towards finger of God.
Exactly, that's right.
Yeah,
That's
so you have the kinetic velocity of particles will be more dominant compared to the
right.
peculiar
Yeah,
velocity due to the gravity.
exactly, that's right.
Yes.
Yeah,
Yeah.
thanks. Yeah.
Yeah.
Kananda, what are the length scales or K modes where these three effects are important?
Okay, so let me go to the results section again. So Alcock-Paczynski, I don't know. No one has done it. For light cone and red C space distribution, I can tell you. Yeah, so you see this plot for light cone, it's mostly less than 0.1 in this, if you believe this in our simulation. So it is 0.1 or maybe 0.2 or less. That is where light cone is very strong. Red C space distortion, again, if I go to this plot, yeah, so you see this plot. So red shift space distortion. Here I show results for 3 K modes. Again, they are strong at small k, that is 0.03, 0.11, at large k it is getting reduced. But then again, that effect is more, very strong at the early stage of reionization, not at the late stage. So let's say, for example, when reionization is 50% or later, the effect is not even 10%. The changes in part spectrum due to the redshift is not 10%. Hello?
Yes, got it.
Yeah.
And they,
someone has also one paper on that. So yeah, I think they also agree with us for results.
Yeah, means there are many things. Means there is redshift, there is model, there is neutral fraction, there is many things involved. So you cannot pinpoint the scale.
No, but at least my feeling is that at later stage, when you have large bubbles, I think all models predict large bubbles at later stage. Then your redshift prediction is not that strong.
Yeah, means you qualitatively can say, but you cannot quantify which is the scale it is important. So that I'm saying. Yeah.
No, but see, if you don't have a large bubble, then the chip space distortion cannot do anything, right? You need to have a certain size bubble over which it is visible. Otherwise, both the side of the bubble will be at the same redshift almost.
No, person, I don't get your point.
If the bubble is small enough, then the two sides of the bubble are almost at the same evolution stage, right?
Right.
It doesn't take much time to go from one side to the other.
Right.
So the RSD will not be that much.
No, but for when your bubbles are small, that means you are referring to early stage of reionization. There we see very strong effect. What happens that your when your bubbles are small, and all those bubbles form around very high density peak regions, and that means those high density regions are it's a complicated interpretation, but we
we have a distribution of bubble. There is no
RSD. Sorry, I was saying the light cone effect will not be important if you have small size bubbles. Right?
Yes.
Yeah,
So light cone is a large scale effect, and also you see strong light cone at the later stage.
So how fast is the distance changing with redshift and the size of the bubble? These two will probably compete for the light cone effect.
No, the signal itself, the neutral, how fast the neutral fraction is changing, how fast the brightness temperature is changing. That is the determined factor.
No, also the bubble size.
Yes, also bubble, but bubbles is correlated with the brightness temperature. If it is
typical
smoothly varying, then bubble will go gradually. If it is fastly varying, so bubble will drastically change the size. Yes.
I think typical ionization front speed is 10,000 kilometers per second. The speed of light is 3 lakh kilometers per second, so it's much smaller. Ionization front moves much smaller as compared to
Yes, yes, of course, of course. But Prakash, this ionization speed around very strong quasar, that can be very high, right?
Yeah, but then we always assume that the quasars are not the main responsible sources for reionization, right?
Yeah, yeah. But if you look at look at individual quasars.
Yes, exactly. But then the problem is they will also ionize helium too, which we don't see. So helium, I mean, the quasars may not be responsible for reionization, but they are really good for probing the liminal forest.
Right.
Quasars at high redshift, yes.
Right. Now, so we looked at, I think, 2011-12, we looked at this relativistic speed of ionization front around very strong supermassive quasar.
Yes. Correct.
And there we found some interesting effects. So let's say if you have isotopically emitting quasars,
correct.
Of course it is not true, but if you assume it, very strong 10 to the power 9 or 10 solar mass black hole inside.
Correct.
And they emit very brightly. So front speed may be very close to the speed of light. And then
the thing is, those happens only in the proximity region of the quasars, not on the IGM. I mean, when I talk about the ionization front speed, I mean in the IGM, when the bubbles are overlapping. Very close to the quasars, it can happen that the speed of the, I mean,
so initial phase of ionization front growth, yes.
Exactly. That's
and
right.
there those, even if it is a spherical cell, it may appear elongated or compressed because of this light. Yeah. Right. So we studied actually that.
Yeah, agree.
Yeah. Okay, I think.
So Presidency is not studied as much, is it?
In the context of you are not.
21 centimeter.
Yeah, you're. But galaxy context, people have studied it.
Is there a reason why people have not studied?
I mean, it turns out that the FE effect, that has a very small impact in compared to the effect of RST. So that's why it is very difficult to just separate out the effect of Alcock-Paczynski and then the redshift distortion. So one can in principle study it, but it's a higher order effect. Yes.
But if we say selectively choose the regions which has lower density,
but it's the FE effect is coming from the cosmological, wrongly use of cosmological scenario, right?
So if I choose the lower density then regions, then the RSD will not be there, right? It will be very less. The velocity will also be less, right?
But overall effect will be on your this large scale power spectrum. You can't just separate out the low density. You can come to the highly ionized regime where the effect of RSD is low. Like in this picture, when it's above 50% ionization, the RSD effect is low, but the AP effect is also, that impact is also very low. So relative to this effect of RSD, the effect of AP, that always remains quite low. So very difficult to separate out that one.
Not with scale and any other.
No.
Yeah,
no, one second. I was just wondering. So imagine that I can object that I cannot do it, but imagine that I have a map of the sky, and I separate out the regions where I have lower densities.
Right.
Yes.
So there I can there I'll not see much RSD, right? Because the peculiar velocities are also expected to be small because lower density.
Yes.
So in principle, I can now look at the
but your signal will also be small, right? Because
I mean, first of all, like you will not be able to, I mean, this 21 centimeter probe will not work in that way because you are anyway probing a very small part of your sky. So that means you are probing smaller scales. So that part is very difficult to observe in 21 centimeter observations. But in the galaxy surveys, this FE effect, I think, is.
No, 1 second. I am not saying smaller scale. Imagine that you have one of these images that Kananda was showing you in theta and z.
Yes, but in that part of the sky, you are only concentrated on that part of the sky that has low density.
Let me finish.
Okay.
So now I mark out the regions in 3D which has high densities. So I will still have a lot of places in the sky lab which has lower densities. High densities are only pockets, right?
Yes. Okay.
So now on that I calculate my power spectrum, etc. I will have some convolution with this. If I calculate the 2-point correlation function, I will not have convolution. Otherwise, I will have something which I take care of because I know. I mean, I am saying in principle. I'm not saying that you can do it right now.
Yeah, what you
one
are
have to
suggesting
look
is
at
fine,
it.
but it's very difficult to. I mean, in experimental setup to do this particular thing which you are explaining. This is not trivial. Maybe if someone can do in experiment, then of course in that part the effect of RST will be minimum. And what I mean, we also have like bound what wrong cosmology we can choose. Like there are these observations and they have this error bar on those cosmological parameters. So yeah, I mean, you can't just choose a very wrong cosmology where your effect of AP will be quite drastic. So the extreme model which you can choose within this error bar of, let's say, the Planck error bar limit, that doesn't show a high impact of FE effect. The overall, the cosmological signal map. But what you are proposing, that, I mean, I don't know how to set up that particular scenario in observation. But of course, yeah, I mean, what you are suggesting is correct. The effect will be low.
See, observationally, you cannot say whether it's a high density or low density region. What you can say is it's a highly neutral or ionized region, right? It may happen that there is a low density region, but it's highly neutral because the ionization front has not reached there. So as a result, you will say that it's high density, but it's not actually high density.
But again, I probably misinterpreting this one. The low density region that will appear more low density region in if you add the RST effect.
Yes.
So the effect will be there eventually. The effect of resistance distortion.
Exactly, but then how can you separate the high density region from low density in the observations? Because what you get is only neutral or ionized region, right? In the observation.
I mean,
we'll get brightness temperature. We'll get finally brightness temperature. We will not get
for that you need other surveys like galaxy surveys where you assuming that those are formed in the high density regions.
The other thing is, I mean, we are talking at redshift of 7 or 6 or 8, right? At this redshift, the structures have not formed much. So there is not much clear distinction between the very high density region and IGM, right? Because structures have not evolved much. At least that's what the slices that Kanan has shown reveals, right?
I'm not sure.
I mean, there are not many structures that have formed at very high redshift, right?
No,
I mean, the number density of sources will be low.
Yeah.
Mm-hmm.
I mean, we'll have definitely we have halos, but the number density of sources will be low compared to the lower.
Enough density to have RST at those, obviously.
Yeah, of course.
Yeah, no, you can extrapolate the mass function and see.
Like if your IgM is completely neutral, the effect of RST that will boost all scale power spectrum to with a factor of like 2. So the effect is always there, the effect of RST. So the high dense region, whether there are sources or not, they will appear more dense, and the low dense region, they will appear more, low dense, lower density. Yeah, I mean, that will boost the power value, but that will be in all scale what is probed in 21 centimeter observations.
Yeah, and one thing, Prasunda and Rajesh and Kananda also. So I just checked, I think there was one paper by Adi Nasir. So he has studied this effect of alpha Presidency on redshifted 21 centimeter maps. So possibly we can have a look at it, if possible.
Yeah,
So,
there
yes,
are few.
yes.
There are few, but not extensive study has been done.
Yes, that's true.
I mean, yeah, I mean, he had studied this one, but like using that idea to use in precision cosmology to constant your cosmological parameter, that concept is very difficult. And in reality, it is kind of impossible as the RSD is present. If the RSD is not present, then probably we can use that idea for precision cosmology and constant or cosmological parameter.
And nowadays the cosmology has so precise, means you cannot do, means the hand is bound. Means you have
No. See. I mean, the point is well taken. That is very difficult to do, but you want to do cosmology. I mean, see, one point of doing redshifted 21 centimeter observation is also to see if the lambda parameter changes along Z. Yeah, cosmology is not known. If you have dark energy, etc.
Yeah. I mean, this is a completely different approach. Like you choose your different cosmological parameters that will affect in your density and halo list and things like that.
The scale.
See, Hubble parameter value also is not settled yet.
Right.
Yes.
So, this effect cannot be used. That is the bottom line.
No, so you don't know your cosmological parameters very precisely. I mean, people believe in lambda CDM, but
you see, our telescope is sensitive below 0.1, basically 1 or So at those scale, basically, we cannot distinguish this effect. And mostly the Alcott so this effect is very less, you can say.
So I think the bottom line is that one can do preliminary study. I mean, there is
Yeah, of course. This topic is open.
Without studying.
Yeah, no one has done it, and if you write a paper, it will be accepted for sure. Okay, thank you for so many discussion and questions.
Thank you.
Yeah, thank you, Kananda, for elaborating on this topic, and it's very interesting. And thanks everyone for joining today.